300 meters beneath the surface of the ocean, in a steel cylinder with no way up that does not take minutes, there is a fire that is never allowed to go out. It is not a fire in the ordinary sense. There is no flame, nothing burning, no air being consumed, but it produces heat on the scale of a small power station continuously, for years without pause, inside a sealed compartment that a crew has to live pressed up against. And here's the part that does not sit easily once you understand it. That heat source, the thing keeping more than 100 people alive down there by turning a propeller and making their air and their water, is also the one thing aboard that they can never fully switch off, never walk away from, never allow to simply stop. A car engine can idle, a ship's diesel can be shut down at the pier. This cannot. Stopping it, really stopping it, is a procedure measured in the physics of decay heat, not the turn of a key. The reactor is what keeps them alive. It is also the thing they are least able to control on their own terms. How a machine gets built to be that reliable and what happens on the one occasion the chain does break is the subject of this. Start with the assumption almost everyone carries, because it is wrong in a way that matters. People think of a submarine reactor as a bomb that has been persuaded to behave, a violent thing held on a tight leash, one slip away from disaster. That picture is exactly backwards. The engineering that went into a naval reactor was not aimed at restraining something eager to run away. It was aimed at the opposite problem, at building something that would refuse to stop running when the crew needed it, that would keep making heat steadily through decades and battle shock and crash turns and every abuse the sea could apply, and that would fail when it failed at all in the direction of safety rather than catastrophe. The whole design philosophy is about reliability under conditions no land reactor ever faces, because a land reactor that shuts down is an inconvenience, and a submarine reactor that shuts down at depth can be the end of the boat. So the counterintuitive truth is this: the danger to the crew was almost never the reactor itself. In the entire history of the United States Naval Reactor Program, across more than 6,700 reactor years of operation, there has not been a single reactor accident that released radioactivity, not one. The things that have actually threatened these boats came from somewhere else entirely, from the ordinary plumbing and the ordinary seawater, and we will get to the night that proved it. There are 4 things worth understanding to see how this works: what the heat actually is and why it cannot simply be turned off, how the reactor regulates itself without anyone touching it, how the plant is built in 2 separate halves so the crew can stand next to it, and why a machine designed to run for 30 years still, at the very end, has to be dealt with in a way that says a great deal about the whole enterprise. 4 systems, and behind all of them, a watchstander who has to notice a number changing. If this is the kind of thing you would spend an hour on, the channel is built for exactly this, so consider subscribing before we go below. We begin with the heat. The heat comes from splitting atoms, and the important thing to hold is that this is not burning. Combustion needs oxygen and produces flame and can be starved and smothered. Fission needs neither. Inside the reactor core, atoms of uranium are struck by neutrons and split, and each split releases energy and more neutrons, which go on to split more atoms in a chain that sustains itself as long as the conditions allow it. That is the source of the heat, and it is why a submarine can stay down for months while a diesel boat has to come up for air every day or two, because the reactor consumes no oxygen at all. It makes its heat in a sealed loop that owes nothing to the outside world. But that same independence is the reason it cannot simply be switched off like a flame. When you insert the control rods and stop the chain reaction, you have stopped the fission, but you have not stopped the heat. The material in the core has been producing fission products for months or years, and those products continue to decay and continue to give off heat for a long time after the chain reaction is halted. This is called decay heat, and it is not a small effect. A reactor that has just been shut down is still producing a significant fraction of its thermal output, and that output has to go somewhere, has to be carried away by coolant that keeps flowing, or the core will overheat even with the reaction stopped. So shutting down a naval reactor is not an event. It is a managed descent, a process of removing heat faster than the decay produces it, holding the plant while it cools over time. You cannot slam the door. And now hold on to the number that reframes the whole problem, because it is the number the crew actually lives by. The reactor is held under enormous pressure, on the order of 2,250 pounds per square inch, and it is held there for a very specific reason. The water in the primary loop runs at around 250 to 300 degrees Celsius, which is far above the temperature at which water would normally boil. It does not boil because the pressure will not let it. That is deliberate. Water that stays liquid carries heat away far more effectively than steam does, and the entire cooling of the core depends on that water remaining liquid as it moves, which means the pressure is not a hazard to be feared. It is the thing doing the work. Take the pressure away and the water flashes to steam and stops cooling the core at the exact moment cooling matters most. Think of a pressure cooker on a stove, water hotter than boiling, and still liquid only because the lid holds the pressure in. The reactor is that principle carried to an extreme and built to hold it for 30 years. That is the danger the design actually answers to, not an explosion, but the loss of the conditions that keep the coolant doing its job. So here's the inversion, the single fact most people never hear, and it turns the frightening picture inside out. The reactor does not need a person standing over it to keep it from running away. It is built so that the physics itself pushes back against a runaway, automatically, with no human action and no moving parts involved in the correction. This is called a negative temperature coefficient of reactivity, and the idea underneath the intimidating name is simple and elegant. As the reactor gets hotter, the reaction naturally slows down. The rising temperature itself reduces the efficiency of the chain reaction. So an increase in heat produces a decrease in reactivity, which reduces the heat, which is a loop that settles rather than a loop that escalates. The reactor tends towards stability on its own. If the power tries to surge, the temperature rises, and the rising temperature damps the surge. You do not have to catch it. The physics catches it. And this is not a bolt-on safety feature. It is engineered into the fundamental design of the core, chosen deliberately over arrangements that would not behave this way, because a naval reactor has to be safe in the hands of a crew who are also fighting a ship, and the only protection you can fully trust is the one that needs no one to remember it. Now layer a second piece of cleverness on top of that, because it answers a question you might not have thought to ask. If the core is loaded with enough fuel to run for decades, why does it not simply burn far too hot at the beginning when all that fuel is fresh and then fade? The answer is that the designers put poison into the core on purpose. They incorporate materials, things like gadolinium and boron, that absorb neutrons, and they distribute them through the fresh fuel so that early in the core's life, when reactivity would otherwise be far too high, these burnable poisons soak up the excess. As the years pass and the fuel depletes, the poisons deplete too, releasing their grip at roughly the same rate the fuel weakens. The two effects are tuned to cancel, so the reactor holds a roughly steady output across a span of years that would otherwise see it flare and die. It is a chemical clock built into the metal, designed to run down in step with the fuel, and the operating limits the crew work to are not set at the edge of danger. They are set far inside it with enormous margin, because the program that built these plants treats margin as the entire point. The limit is not there to keep the crew barely alive. It is there so the dangerous condition is never even approached. That philosophy, conservative to the point of obsession, is the response to the heat, and it leads directly to how the plant is physically arranged, because reliability in the physics means nothing if the crew cannot survive standing next to it. Look at how the plant is built, and you are looking at a decision to keep two things completely separate that a simpler design would have joined. A naval reactor is a pressurized water reactor, and it runs in two loops that never mix. The first loop, the primary, is the water that flows through the core itself, the water held under that great pressure, and this water becomes radioactive as it passes through the core. It is the hot, dangerous water, and the entire design ensures it never leaves the shielded reactor compartment. It circulates from the core to a component called a steam generator and back, a closed circle sealed inside the shielding. The second loop, the secondary, is separate water that runs through the other side of that same steam generator, picking up heat through the metal walls of the tubes without ever touching the primary water. The secondary water flashes to steam, and it is that steam, clean and free of radioactivity, that leaves the compartment to drive the turbines that turn the propeller and spin the generators. The two loops share heat and share nothing else. This is the arrangement that lets a crew live aboard. The radioactive water stays behind heavy shielding in its sealed compartment, and only the clean steam comes out to do the visible work. Between the crew and the core sits a deliberate wall of shielding, enough that when the reactor is shut down, the compartment can be entered, and the whole geometry of the boat is built around keeping people on the right side of it. Now notice a component doing a second job you would not guess. The pressurizer, the vessel that holds the primary loop at its enormous pressure, does that by keeping a bubble of steam above a body of water and heating or cooling that bubble to raise or lower the pressure on demand. Its first job is to hold the pressure that keeps the coolant liquid. But that same ability to expand and absorb changes in volume is what lets the plant ride out the sudden swings of a warship in operation. The crash changes in power. A submarine demands when it maneuvers, without the pressure lurching out of its safe band. One vessel, two functions, holding the line and absorbing the shocks. And here is the detail to hold on to, because it will matter later in the cold water off Cape Cod. Every one of these loops, primary and secondary, is a system of pipes, and every pipe is a series of joints, and how those joints are made, whether they are brazed or whether they are welded, is not a trivial distinction. A joint is a place where a system can fail. Keep that in mind. The seawater systems that cool the plant and serve the boat run at the pressure of the sea outside, and at depth that pressure is immense, and every joint in every one of those lines is holding it back. The plant can be perfect, and a joint can still let go. Which brings us to why a machine built to run for 30 years still has one appointment it cannot escape. Here is the thing the reliability hides, and it is the second inversion of this story. A naval reactor that must never be allowed to stop at sea must nonetheless eventually be stopped completely, opened and refueled, and for most of the history of these boats that was one of the largest and most disruptive events in the vessel's life. The core does not last forever. Over the years, the fuel on the bottom depletes and the fission products accumulate, and the operators compensate by drawing the control rods further and further out to expose more fuel, until a point arrives where there is simply not enough workable fuel left and too much poisoning from the accumulated products, and the core can no longer make heat efficiently. It has to be replaced, and replacing it on the older boats meant something drastic. It meant cutting through the pressure hull itself, opening the submarine up to reach the reactor compartment, removing the spent core and installing a fresh one, a process that took the boat out of service for the better part of 2 years and cost in the range of many hundreds of millions of dollars. The submarine that must never stop had to be sawn open to be kept alive. The earliest boats needed this every handful of years. And response to that, across decades of patient engineering, was to push the interval out and out until it disappeared. The enrichment of the fuel was raised far beyond what any civilian plant uses, up toward and past 90%, packing far more energy into the same small core. The burnable poisons were refined to hold reactivity steady across longer and longer spans, and the result, on the newest classes, is what the engineers call a life-of-ship core, a reactor fueled once, at construction, and never opened again for the entire service life of the boat, 30 years and more. The vessel is welded shut around it and stays shut. Now walk the defenses that keep the plant alive when something does go wrong. Because they run from the sophisticated down to the crude, and the crude one is the one that saves you. At the top sit the automatic systems, the instruments watching dozens of parameters continuously, neutron levels and temperatures and pressures and flow rates, any one of which crossing a limit will trigger an automatic shutdown, a scram dropping the control rods and stopping the chain reaction in an instant. That is the sophisticated layer, and it is fast and it is reliable. But a scram creates its own problem, the very problem we started with. It stops the fission, but the decay heat remains, and now the reactor is shut down and still hot, and the boat may have just lost the propulsion it was depending on. So beneath the automatic scram sits a cruder, more human layer, the procedures for what the crew does in the seconds and minutes after. And the single most important lesson in the history of these plants is about exactly that layer, and it was bought at a terrible price on one morning in April. It was the 10th of April, 1963, off the coast of Cape Cod, and there was no battle within 1,000 miles. The submarine was the Thresher, the lead boat of a brand new class of fast attack submarines, less than 2 years old, the most advanced vessel of her kind in the world. She was conducting deep diving trials after a period of maintenance in the shipyard, with a surface ship standing by above her on the underwater telephone. She dove toward her test depth, 1,300 feet down, and somewhere in the after part of the boat, a joint in a seawater pipe let go. Remember the joints. Remember brazed against welded, set down earlier with a note that it would matter. This is where it matters. The investigation that followed, which produced more than 1,700 pages of testimony and has since been largely declassified, concluded that a silver brazed joint in a seawater system, rather than a welded one, most probably failed under the full pressure of the sea at that depth. Seawater sprayed into the engine room. It reached an electrical panel. The short circuit that followed triggered an automatic scram of the reactor, exactly as the automatic system was designed to do. And in that instant the boat had a flooding casualty and a reactor that had just shut itself down, and the decay heat problem we described at the start, all at the same moment, at depth. Under the procedures in force at that time, steam flow was to be secured after a scram, which meant that at the moment the crew most needed propulsion to drive the boat back toward the surface, the stored energy in the plant was being shut away rather than used. The submarine could not recover. She was lost with all 129 men aboard, sailors and civilian shipyard workers, and she broke apart below her crush depth. Nothing in that chain was exotic. A joint made one way instead of another. Water on a panel. An automatic shutdown doing precisely what it was built to do, at precisely the wrong time. Ordinary things, assembled in one order on a routine test dive, becoming irreversible, and the change that came out of it reshaped the entire enterprise. It created the Submarine Safety Program, SubSafe, a quality assurance regime governing the design, the materials and the testing of every system exposed to sea pressure, with documented objective evidence required for every critical joint and component. The brazed joints gave way to welded ones under rigorous control, and the operating procedure was changed for every nuclear submarine in the fleet to allow the crew to use the heat energy stored in the plant for emergency propulsion while the reactor was being brought back, rather than securing it. Testing later proved the plant could have dragged steam from a scrammed reactor for more than 20 minutes without harm. The margin had been there all along. The procedure had simply forbidden its use. Since SubSafe, no submarine certified under it has been lost to flooding or structural failure. The men of the Thresher bought that with their lives, and the record since is the receipt, which leaves the part of the whole system that was never engineered because it could not be. Everything we have described, the self-regulating physics, the two sealed loops, the automatic scram, the shielding, the life of ship core, does exactly what it was built to do and not one thing more. None of it decides. The scram does not know whether the boat needs propulsion at the moment it drops the rods. The negative temperature coefficient does not know there is a crew. The pressurizer holds its bubble whether the news is good or bad. So the program that built these plants did something unusual. It decided that if the last line of defense was going to be a human being, then that human being would be selected and trained to a standard almost without parallel. Under the Naval Reactors Program established by Admiral Rickover, the people who operate these plants are drawn from the top academic performers and put through something close to 2 years of training before they stand a watch alone. Nuclear power school, and then months on a land-based prototype plant learning the real thing under supervision. And a specific piece of that training traces directly back to the Thresher. Reactor fast recovery, the drilled procedure for bringing a scrammed plant back quickly and using its stored heat, is taught to every submarine qualified crew member on every class, a designed human response to a known failure mode, sitting in the architecture in the same place as a relief valve. The training is not sentiment, it is a component, and the environment those people work in does its own quiet work on them over a long patrol. Buttoned up for weeks or months, there is no daylight and no weather and no horizon. Only the same filtered air and the same instrument glow and the same hum of the plant, watch after watch, and the reactor never resting means the watch never resting either. Someone is always awake in front of those panels, and the honest pattern, the one the whole record shows, is that when these boats have come to grief, it has almost never been the reactor that failed. It has been a joint, a valve, a panel, a procedure, an ordinary thing, and the defense against ordinary things going wrong in the wrong order is a person who notices a number drifting before it becomes a casualty. The panel displays, it does not conclude. The concluding is still done by someone standing a watch 300 meters down, reading a gauge, in a compartment built so that catastrophe cannot assemble itself out of any single failure, except the one failure the machine can never cover, which is a person not noticing in time. So count the 4 again, quickly, the way they actually stack. The heat is fission, not fire, and it cannot be switched off, only managed down through its own decay. The reactor regulates itself. the physics pushing back against a runaway with no hand on the controls. The plant runs in 2 sealed loops so the crew can live beside a radioactive core behind shielding. And a machine built to run for 30 years is now built to run without ever being opened. It's one unavoidable appointment engineered almost out of existence. 4 systems. And the 5th thing we named at the start now has a face. It is the Watchstander who notices the number. Go back to the image we opened with. The crew pressed up against a heat source they can never fully switch off, 300 meters down with no quick way to the surface, and you can see it differently now. That is not a leash barely holding. It is the most reliable machine ever sent to sea, built by people who decided that reliability, not power, was the thing worth chasing, and who proved across 6,000 reactor years that they were right. The reactor was never the thing most likely to end the boat. The pipe joint was. And the answer to the pipe joint, in the end, was not a cleverer pipe. It was a program that wrote down in the plainest possible terms what must never be assumed again, and a watchstander trained to catch it if it is. If you want to keep going inside machines like this one, the ones almost no one is allowed near, that is the whole reason this channel exists. So subscribe and stay with it. The next one climbs into the launch tube of a ballistic missile submarine, into the compartment where a crew lives for months alongside the one system they hope never to use. And the strangest part is what has to be true, physically and procedurally, before it can be used at all. And a question for the comments while you sit with this one. If a reactor is built so the physics itself keeps it safe, and the greatest danger was always the ordinary plumbing around it, then is a nuclear submarine a triumph of nuclear engineering, or a triumph of ordinary engineering done to an extraordinary standard, and are those really different things? There is a real argument on both sides, and I would like to read yours. This video is for educational purposes only. It draws on published engineering literature, declassified documentation, manufacturer and service publications, and investigated peacetime incident reports. Where a figure is an outside estimate or has never been released, this is stated, and where practice varies between services or jurisdictions, this is noted. Nothing in this video is operational guidance.